It's a great opportunity to introduce Kathrin and meet her digitally here again. So Kathrin and I are maybe on a similar state in our academic careers. Both started our tenure track professorships at rather similar time. So Kathrin is a tenure track professor for digital fabrication at TU-München, and previously has been a researcher at the NCCR at the ETH Zurich at the group of Ramazzo and Kohler, where she also conducted her PhD research. Yeah, her work is very much focused on on-site robotics, collaborative robotics, in situ fabrication, human-machine collaboration, and augmented reality. And so matching those different spheres. And in the context of the symposium, additive fabrication, Kathrin has used the robots to do a lot. She had the robots lay bricks, throw clay, print concrete, and we're happy to see what she presents here today. Thank you for joining us.
Thank you for a nice introduction. I'll try to share a screen now and hope. Okay, so hello and thank you for the opportunity to present at the BE-AM Symposium on the topic of employing collaborative mobile robots for additive manufacturing directly on building sites. As said, my name is Kathrin Dörfler. I'm tenure track professor for digital fabrication at the TU-München School of Engineering and Design. The research I'm presenting here today is part of the collaborative research center TR 277, Additive Manufacturing in Construction, which is funded by the DFG and which is conducted in between the Technical University of Munich and the Technical University of Braunschweig. And the research I'm presenting today is led by Guido Dielemans, doing his PhD in my group on this topic. I was quite long thinking what to present to you here today, as we are suffering some many COVID cost delays in producing first results of this research. As such, this will be a work in progress talk, more questions than answers. So please, everybody who came here for answers, you can drop in later. So I will start with an extended introduction of the research area of mobile AM, starting with some prior work and also with the motivation why we think that particular topic is interesting. In the domain of mobile AM as background for our own conception and design of two research platforms, some experimentations around or beyond mobile AM, and after which I will close with some conclusions to open some discussion. So as you all know, the way we produce things is drastically changing, in particular in the manufacturing industries. Automation and additive manufacturing production methods allow us to produce bespoke goods and products in a very labor and also material efficient way today, as you would see also in a range of presentations today. But is the way we build our buildings also changing today, and particularly on building sites? And importantly, if so, who will also drive this change? This year, in the urgency of climate change, Ursula von der Leyen's EU initiative for a new European Bauhaus was published, as probably all of you heard, with the help of which she proclaims the necessity to transform the current construction sector from a carbon source into a carbon sink. What is particularly interesting about her message is, and what resonates very much with our group's ideas, is her open commitment to design as a cultural good. So this new Bauhaus must not only be an economic, ecological, or technological project, but a sort of new cultural project for Europe. So what can digital fabrication do in this domain? We see digital fabrication as a very integrative platform to connect architecture and design with robotics and fabrication technology to fundamentally rethink and transform the way we build. And in this context, robots and new technologies are not merely tools for rationalization and automation, but rather they should enable us to find like new ways. So when we look at today's machines, they are not purely mechanical. They can be programmed digitally, and they are connected to sensors and intelligent control algorithms, which in fact radically expands the flexibility, autonomy, and range of applications. Thanks to such an increased autonomy, we can not only use robots in very controlled and structured laboratory environments and assembly lines, but also in uncontrolled ones, such as, of course, construction sites. where mobility, perception, and context awareness enables construction robots to deal with uncertainties and unpredictable events in their immediate surroundings, and also with the materials they are processing. So during my PhD at TU Zurich, we demonstrated this approach as part of the research building of a residential unit named the DFAB House, in which a custom-made reinforcement concrete wall was built as the main load-bearing element by such a mobile robot. In this process, the reinforcement mesh was fabricated in vertical layers by a mobile robot called in situ fabricator. And as opposed to typical horizontal layers known from 3D printing, that mesh expands in the direction of the movement of the robot. To enable the mesh to be fabricated accurately, the sensing solution consisted of two parts. The first one allowed the robot to be localized by registering April-tag fiducia markers mounted at the wall's foundation. And the second one would actually serve the fabrication itself to allow the mesh contour to be registered to compensate locally for two main sources of error. First, the local deflections of the mesh coming from the material, but then also inaccuracies coming from the global robot's localization. We could show that this robot, which was built from off-the-shelf industrial components, could be brought on site to fabricate this bespoke steel reinforced mesh into a predefined three-dimensional shape. The geometry of this S-shaped wall was locally undulated to increase its structural depth and also to decrease its cross-sectional width. So again, this idea to sort of minimize material consumption. Here you can see the stepwise sort of fabrication of the mesh, similar to 3D printing, just that in this case, a wire is sort of welded with resistance welding to the layer beneath. And the mesh is fabricated with such a density that it acts both as a form-giving element for concrete to be filled in and as reinforcement after the concrete has hardened, so that no traditional formwork is required. So this is the finished reinforcement mesh, and then the finished structure, where you can see also how the other building component, the so-called smart slab of Benjamin Dillenburger's group, is sort of resting on the wall, and the interface produced quite precisely with this sort of shadow gap. So while we could show in this project that it's in principle possible to use a mobile robot on site, we should of course advance our research into this direction, not only because we can, but why should we actually further develop and use mobile robots for building construction, and in particular in situ additive manufacturing processes. So we believe that in comparison with stationary systems, mobile robots present vast new opportunities for actually additive manufacturing, with new possibilities for architecture in terms of an unbounded work area, so manufacturing of building components larger than their static range of the system, scalability and parallelization. So mobile robots could provide scalability with multiple cooperating robots working in parallel, indirect or also indirect interaction with humans, and of course building within existing contexts, so renovating, retrofitting, repairing, and maintaining. The construction methods that are usually associated with the aim of increasing or maintaining value are still largely ignored and undervalued in the context of architecture and digital fabrication. And while stationary on-site robots are largely limited to new constructions on vacant lots, mobile robots could flexibly access enclosed spaces and could thus be useful for future tools for our buildings and infrastructure. So in definition of the architectural design space of in situ AM processes, interactions across four main aspects of autonomous building systems shall be considered. So first, it's the contextual conditions, defining where construction will take place and the accessibility of that location. Then, of course, the structural requirements and morphology of a building. Then itself, the material properties and processes, including the materials that form the structure, as well as those that are incorporated as part of the additive manufacturing process. And then lastly, also, of course, the mechanical system. So in essence, the robot, the fabricating system that transports, manipulates, processes, and deposits material at specified locations, creating the building structure by compounding material. So in this context, various companies and research institutions have developed different robotic systems in the last years that range from mobile systems with an extended manipulator, covering a quite wide range workspace, to mobile systems with a sort of standard manipulator covering a mid-range workspace, to very small scale and tiny robots with sort of no manipulator and therefore a very short range workspace. This range of spectrum has been shown very impressively by the mediated matter group from MIT, ranging from very large robots, as shown with this digital construction platform, with a wide range reach envelope, which can be used for 3D printing building scale structures in a sort of quasi-stationary manner. But also to very tiny robots, in this case, they're called the fiberbots, which have to continuously move while manufacturing these tube-like structures in order to sort of create a bigger structure. With multi-degree of freedom manipulators mounted onto mobile bases, such as an anthropomorphic robotic manipulator with 6 axes of freedom, shown here with the 3D printing system by the NTU Singapore. The reach envelope is located somewhere in the middle, so, but more importantly, extended printing configurations can be considered that allow for better transfer of forces and contact area between layers. One of these techniques is the tangential continuity method, which was shown also this morning by Philip Block. In sum, the higher the mobility of a robot, the higher the requirements for autonomy and context awareness are, which in fact for us is still the most interesting, but also the most challenging point of all. So a robot must be able to be aware of its surroundings. It must be able to locate itself within these surroundings. It must be able not only to react, but to physically interact with its environment, and also coming from a building plan with high geometric precision, and also to coordinate its tasks with other robots and potentially humans. So in the last year, we have been designing and putting together our own research platform, 2 collaborative mobile robots to pursue research within the Sonderforschungsbereich TR 277 AMC with the following components. For manipulation of the end effector,
we lost you there, Kathrin.
I think she was kicked out entirely, wasn't she?
Oh, I was kicked out, I think.
Yeah.
Still in the meeting.
Yeah, you're in the meeting.
But
Yeah, I just saw somebody knocking on my door. Can you hear me?
Yes, we hear you.
Ah, okay. Then I will try sharing screen again.
I think we lost you in the last couple of slides of your presentation.
Oh, really? Okay. Can you see my screen again?
Yes, we see the screen.
Okay.
We see a research platform.
Yeah. Can you tell me where?
I would say it's maybe 1 slide back.
Here?
Yeah, that one, exactly.
Okay. So in the last year, we have been, sorry, I need to change again this window that is now in my way. Okay. In the last year, we have been designing and putting together 2 platforms, mobile research platforms, to pursue research within the AMC Sonderforschungsbereich with the following components. So for manipulation of the end effector, we chose a collaborative robot, a Euro10E, which allows for close collaboration and proximity with humans. Then an omnidirectional movement system with 4 steerable wheels, which was chosen to allow simplified maneuverability over building sites, and it is able to avoid obstacles in various configurations and supports sort of smooth transitions in tight areas. Also to support building scale, a vertical axis was included, which allows the robotic manipulator to achieve ceiling height. Then onboard material supply for clay was considered, or also an offboard material supply with a continuous mixing and pumping system. Then the custom end effector was designed to be lightweight and also to apply minimal strain to the robotic manipulator as it's low payload. And the extruder is actuated to precisely control the extruded volume, which additionally allows for non-continuous print path. And then the first tier of localization is the mobile platform the mobile platform localization in the global coordinate system of the worksite. In this case, with a RoboSense beeper lidar using a hemispherical field of view. And then the second tier has the end effector equipped with a line laser scanner to determine the profile and also the distance to the actually additively manufactured workpiece. So in close collaboration with other projects from this cluster of research AMC, we here aim to explore the design space and opportunities of this technology on architecture and construction. And to provide more emphasis on the process rather than the material system of concrete, we first opted for equipping the mobile system with clay extrusion for constructing clay structures to be used as reusable formworks for the construction of larger scale building components. Last academic year has seen some small scale experimentations with students on the robotic clay extrusion system, where we try to explore the shape of the potential as well as the collaborative printing approach, as well combinations of assembly and printing and so on. So, which we hopefully will soon be able to test in real scale scenarios, as we have been given some preview from our soon-to-be new team member from the integrated city in Spain. Yeah, of course, we're looking forward to new next steps in experimentation. So to close this talk, another for us very exciting side product of developing design strategies for mobile robots is that the context awareness that mobile robots require is actually exactly the same technology that is used by AR-related technologies. Hence, we see mobile AR and mobile robotics for building constructions as very tightly coupled and sort of seen in combination. So I would like to introduce a small research project named LOGS, where we investigated, instead of using robots, if and how people can collectively and collaboratively build a pavilion, simply by following step-by-step building instructions visualized via AR on mobile phones. So LOGS is the outcome of a research-based design studio together with our students, and it's a cooperation between our professorship and the Professorship for Structural Design, Pierluigi D'Acunto, and Zurich-based startup Incon AI, Instructive Constructive. Timothy Sandy as the sort of founder of the startup. We built a pavilion with the system that has been shown as part of the Kunstareal Festival here in Munich at the south lawn of the Alte Pinakothek this July. In the setup of LOGS, digital building instructions can be retrieved by multiple users via a mobile AR app, which positions building instructions in 3D space. And the whole research questions was somehow revolve around how the construction progress can be synchronized and coordinated via the app using cloud-based tools to allow not only one user, but several users to participate in the construction at the same time. And I'm just kind of sharing this video with you. Stop talk because
with LOGS, we enable collaborative building using augmented reality tools. The project is a cooperation between the two professorships of digital fabrication and structural design and Zurich-based startup Incon AI. In LOGS, the users can retrieve building instructions via the mobile AR app, which superimposes the building instructions over the physical structure.
Participants can log in as users by pointing their phone to any QR code to visualize the digital model of the pavilion overlaid on the physical structure. By doing so, they will shown the instructions on how to participate in the building the model, as well as specifically the elements they can build visualized in green. They can choose and select any of these elements to their wish, and once this element is placed in the real world, they can set this as build, and this action will unlock new buildable elements visualized on the screen.
By following these instructions, users can build complex structures without the need of additional measurement tools or printed plans.
This coordination will enable multiple users to participate building the LOX pavilion together at the same time.
So we developed the project as part of our design studio last semester, and the initial idea was to create a building system which would consist only of a single element that would offer a variety of interlocking connections. And our main inspirations were games for children and wooden blocks for children, and we kind of scaled it up for adults to create a kind of a playful and creative project.
For the Kunstareal Festival, we developed this specific design, resembling a weaving pattern that is also enhanced by the use of color. The structure does not only employ the material as a building material, but also as a support during the construction. After the event is over, we will disassemble the pavilion and we will rebuild it at the campus of TU, of course, with a new design.
Based on the principle of topology interlocking structures, LOX offers a variety of form-fitted connections that make use of only one component type. This component type is made of timber and due to its interlocking mechanism does not require any additional connection elements in order to assemble different or multiple elements together.
LOX is shown for the first time at the Kunstareal Fest in Munich, in which we collaboratively built a pavilion together with our students. The overall aim of LOX is to make building processes more tangible and accessible to the public and to encourage community participation. In order to create a sense of belonging and responsibility in our cities, one can imagine that systems like LOX will enable residents to build and rebuild their own jointly created structures for and by themselves.
Okay, Emma's still here. Then I continue with a few just impressions from the exhibition. Come visit us in beautiful Munich sometime. This is the old Pinakothek in front of the university. Yeah. So in conclusion, let me briefly restate a few points where while there are many technological challenges ahead, which require us to basically intensify interdisciplinary collaborations, our research tries to formulate sort of an alternative vision of fully automated building design and robotized construction. Instead, we try to advance on the idea of a hybrid, mutually augmented human-robot work team to, in the future, provide greater flexibility, design freedom, application spaces, also social sustainability of digital fabrication in the built environment. Okay, thank you, and let's keep in touch.
Yes, thank you, Kathrin. Great presentation. Really good to see. So one question that I would have, it's two domains, right? So one is maybe a more technological one, and one is more about the cultural project that you mentioned in the beginning, yeah? Which is maybe already opening up to the larger discussion, is we see that, I think within the group of people discussing here, we all showcase our research on full-scale demonstrators. Yeah, we are really showcasing how could it look like, how does it work technology-wise, and still we don't see too much of it going out into the building industry. Yeah, and then touching back to the technological question, your cyber-physical processes really gather a lot of understanding of what's going on the site, assembly, fabrication of the components. Can this data be gathered for more integrated online certification processes, let's call it, yeah, to maybe circumnavigate the whole big question about how do you certify such individualized, unique, and until now unregulated building systems, which is a big hurdle of actually bringing them into the market, yeah?
Are you talking about norms and sort of quality control?
Yes, for example.
Yeah. Well, here actually, again, technology would already provide the solutions to this. It's just, I really think it's user acceptance, and sort of, it's not that's what I'm saying. It's not just technological question. It's really just also question of sort of, and also I think Philip Lockenmorin said that crisis requires to, or sort of is a driver for trying out new things, as there's a necessity to do so. And for instance, quality control by digital processes can be done because we have a digital twin. We can constantly monitor as the fabrication proceeds. We can store the information, and we can actually use that much more precisely actually than in any manual production method to sort of certify our building processes. Yeah. I think. I don't know. I see Ulrich.
No, it's you're absolutely right. When I was say starting this activity in my civil engineering environment in Darmstadt, obviously this question comes directly, and then you start talking to DBT, the German authority for building products, and they say, well, there's no market. We need $1 million to get this started. But this say concept of scanning what we do, what is the quality, which actually is somehow equal to the concrete setup. You take a part of the concrete, you test that, you get a certificate for that quality which is built. That's something which is really interesting. And I remember other research projects where Chris was involved when they started videos taping the whole production process, and by that really knowing the quality. So say what we read here is this detecting position, allowing the machine to know where it is and what it can do, then using this opportunity to manufacture something, and in parallel evaluate and document the quality. That's that's for free. That's for free. You may name this digital craftsmanship just as digital craftsmanship with well, a limited amount of labor being combined.